So this is section 5.4, and we're just going to do the first part of 5.4 where we're talking about finding the derivative of exponential functions. So the most basic exponential function will be e to the x, the one that we're going to deal with. So I'm going to say this slowly. So if y equals e to the x, then the derivative is, I want to make sure you stay caught up because this is kind of involved, all right? So the derivative of e to the x is itself. That's the significance of the exponential function, is that it is its own derivative function. And then the only thing to think about for this is, well, what if it's not just e to the x? What if it's, for example, e to the x squared? Well, I'm sure you would think that through. Let me scooch that down here so you can see it better, right? Wouldn't that just make it be a chain rule? So the derivative of e to the x squared is going to be itself, but then the chain rule part of it would be to say times the derivative of the exponent, so times 2x. So if you want to write that chain rule kind of as a formula, and you don't really have to, but you could say if y equals e to some function of x, so not just e to the x, but e to the something beyond just x, then the derivative would be itself, so it's still e to the f of x, because that's the exponential part, and then times the derivative of the exponent, so times f prime of x. And that's a very common question that you're going to take the derivative, but there's really no need for us to do examples of even the chain rule version because it's very straightforward. But the way you'll see it show up a lot of times is that maybe an exponential function might be a part of something else. Like look at the first example here. What if I have x times e to the x? If I want to find the derivative, well, e to the x is just a part of a product, so I would have to do a product rule. So the derivative of the first is 1 times the second plus the first is x times the derivative of the second. Well, the derivative of e to the x is just e to the x, and so it's fine to leave it like that. The only thing you might do is maybe factor out e to the x, but whatever, depends on what you need to use this for. Or look at letter B. If I want to find the derivative, well, I have a parentheses with an exponent, so I have to think chain rule. So the derivative it is, so the outside would be bring down the 2, keep the parenthesis, right? Now it's to the first. Now times the derivative of the inside. Well, the derivative of 1 is nothing. There's my minus sign. The derivative of e to the negative x is itself times the derivative of negative x. So times negative 1. I'll just make that be a positive. So again, if you want to do some distributing or whatever, but that's my chain rule. So you just have to kind of be careful with some of the ways they ask you questions. So look at letter C. Find the equation of a tangent line to the given point. Well, we all know, tangent line, I need a slope and a point. They give me the point. So I'm going to need to go in and find the derivative. This is not natural log times e to the x, because remember, ln by it doesn't stand alone, right? This is just a log function. It's kind of like, the log of u. It's kind of like this whole thing is my big giant u. So I could say, well, in order to find the derivative of a log, I have to do u prime over u. Well, in order to do u prime, I'm going to be doing the derivative of e to the x squared. So that is itself times the derivative of the exponent. So times x squared. 2x. So u prime, that's my u prime, all over u. So all over e to the x squared. You might notice on this one, those cancel. And y prime is just 2x. Now, I'm hoping that you noticed that I actually did this the long way. Because what would have been smart at the very beginning, and I wanted to show you that it will still work, but what would have been smart at the very beginning is right here. If y is the natural log of e to the x squared, before I even do the derivative, couldn't I simplify that? Because don't the natural log and the e kind of cancel out? So that whole thing is just x squared. So hopefully it makes sense that the derivative is 2x. And so in this one, I don't even want to leave this because I wanted you to see that this is okay, that you can still get there, but it's way more involved. And the more involved it is, the more of a chance for mistake. So look, whenever you have natural logs and exponentials, look for basic shortcuts. And so in this case, I have one. So that means if I want, so the y prime was 2x. If I want the derivative at -2, plug in, I'm going to get -4. So my equation of the tangent line would be y minus 4 equals the slope times x minus -2. And there's the equation of my tangent line. Okay, look at the next one. It says, find the critical numbers and the inflection points for the following. Okay, so I've got that e to the 3x is being multiplied by this quantity, 4 minus 2x. Yeah, you could distribute to e to the 3x if you want to before you start jumping in, but either way, I'm going to have to do a product rule, so I'm just going to jump in right now. I'm going to say, so the derivative is going to be, derivative of -2 is nothing. Okay, in order to do the derivative of this part, I'm going to do a product rule. So the derivative of e to the 3x is 3 e to the 3x, so derivative of the first. And then the second is the entire parenthesis, so times the second, plus the first, which is e to the 3x. And then the derivative of the second is just going to be -2. And if I want the critical numbers, I need to see where this whole thing equals 0. Well, the best way to do that is let's put this in factored form. So notice I have big ugly term plus big ugly term. So why don't I think about simplifying by factoring? And that happens a lot with exponential functions. You end up simplifying by factoring. So I'm going to factor out an e to the 3x. E to the 3x. So in the first term, I've got the 3 and also the parenthesis. I'm going to go ahead and distribute. So that's going to be 12 minus 6x. Bring down, well, you know what? When I take the e to the 3x out of this second term, all I'm going to have is the -2. So I'm just going to bring down -2. So what I actually have here is e to the 3x times 10 minus 6x. And yes, if I want to, I could factor out a 2, but if I'm setting this equal to 0, let's just look at it. We did an example like this when we were doing the prerequisites stuff. Will this e to the 3x part ever equal 0? No, it's always positive. So the only 0 is going to come from this parenthesis. So what's going to make 10 minus 6x equal 0? Well, wouldn't that be if 10 equals 6x? Or in other words, if x equals 10 over 6, which is 5/3. So there's my critical number. They also said to find the inflection points. If I want to find the inflection points, that means I need to go to the second derivative. So I'll just do the stuff that they asked me kind of in order here. So if I want to go to the second derivative, I'm going to say the second derivative is, and I think I'm going to look at this as my first derivative. So that's what I'll do my product rule on. So the derivative of e to the 3x is 3e to the 3x, derivative of the first, times the second. Oops, sorry, the second would be 10 minus 6x. Plus the first is e to the 3x, and then the derivative of the second is going to be -6. So again, for points of inflection, I want to set this equal to 0, and I think I'll do the same thing as far as factoring. I have a big ugly term here, a big ugly term here, and so I think I'll factor out, why don't I factor out a 3e to the 3x? So in the first term, I just have the 10 minus 6x. I'm going to bring down that minus. And if I take out e to the 3x, and if I also take out a 3, won't that be a -2? So what I actually have here is 3e to the 3x times 8 minus 6x. So again, that e to the 3x is never going to be 0. So this is only going to be 0 when 8 minus 6x is 0, or in other words, when 8 equals 6x. So x is going to be 8 over 6, which would be 4 over 3. So in order to know, so it said find the critical numbers and the inflection points. Well, this is definitely a critical number. this is the potential inflection point. In order to know for sure if it's an inflection point, I need to know if the second derivative changes sign. So I can think about the second derivative. I know it equals 0 at 4/3. If I want to think about if it's positive or negative, again, remember this is always positive. So the second derivative is positive or negative based on this 8 minus 6x. So if you want, you could pick test points. You could say, well, what if x equals 0? That's going to be positive, right? Or if x is 300 million, won't that parenthesis be negative? So it's definitely a point of inflection because the second derivative changes sign, right? So it's definitely a point of inflection. And then the last thing they asked is it says, for each critical number, determine if it's a max or min. Let's assume that says relative max or min. So it's a relative max or min if the derivative changes sign. So you could say, well, here's my derivative. I know it equals 0 at 5/3. Using all the same reasoning, since I know e to the 3x is always positive, the positive or negative is going to be based on that 10 minus 6x. So again, if x equals 0, I've got positive. If x equals 300 million, that parenthesis is going to be negative. So since the derivative changes from positive to negative, I know that there's a relative max at x equals 5/3. So I know that was there was a lot of stuff to talk through, but I just wanted you to talk through how you handle factoring when there are exponentials involved. So that's the first bit of information related to the derivative of e to the x. And in the next video, we'll go into integration involving e to the x.